You're welcome back to our class, Chem Easy International. It's a pleasure to have you back again. And today we are going to be hearkening to the request of our students far and wide concerning demystifying the concept electronic spectra of coordination compounds. In doing that, we are going to be looking at the following subtopics. Introduction. Alright? Whenever you hear electronic spectra of coordination compounds, actually it is as a result of, when you hear spectra or the word spectrum, when you hear spectrum, is a chart. Spectrum is a chart showing you the relationship or the effects of a parameter such as energy on a molecule, the way a molecule will behave with respect to changes in a parameter in a variable such as energy. For instance, we have a compound, we want to take the concentration. We are interested in the concentration of metal ion in an unknown solution. We take it to AAS, atomic absorption spectroscopy or spectrometer, alright, or ICP-OES. So when you are doing that, what will happen is that you are going to be bombarding the compound, the molecule, with energy, with a source of energy. As far as this electronic spectra is concerned, we are interested in UV visible radiation. UV visible radiation will be bombarded against the molecule. Once that happens, there will be excitation of electrons. Such electrons is going to, at the end of the day, at the recorder, at the computer, you are going to print out a result. The result is the spectra. Alright, then how to interpret the spectra. That is what this topic is all about. Alright, and as far as coordination compound is concerned, we're going to be looking at metal ligand complexes. Alright, so we have types of electronic transitions. When you bombard a molecule with a source of energy, UV visible for instance, or visible light for instance, that has a red, orange, yellow, green, blue, indigo, violet, or purple in some cases. When you bombard your molecule with a source of light, visible light, containing these components, what happens actually is that there will be electronic transitions. Electrons will move from one place to another. As far as coordination compounds are concerned, there are three types of electronic transitions that may occur. For my audience, alright, there are some people who call CID. In this class we demystify, we provide mnemonic devices, shortcuts. There are some people who call CID in our environment, alright? Those CID are the different types of what? Of electronic transitions we have, or that may occur when you have, when you bombard your molecule or your compound with what? With visible light. Alright? C is charge transfer. We can have charge transfer. It's a type of what? It's a type of electronic transition under which we have metal ligand charge transfer and ligand metal charge transfer. We'll do justice to this in the meantime. Alright? Yeah, basically it's just, we have metal, we have ligands, for instance, in an octahedral complex. Alright? There may be the transfer or the movement of electrons from this ligand, alright, to the empty d orbitals of the metals. That's ligand to metal charge transfer. There may also be electronic transfer depending on the on the strength, or we call it intensity of the what? Depending on the intensity of the light. This electronic spectra, we can depict a whole lot of things from electronic spectra. We'll come to that in the meantime. So we have charge transfer, MLCT, LMCT. We have intraligand transition. Alright? That is within a ligand. There may be transition. And then we have D to D transition. Alright? D to D. You know, metals, especially transition metals, they are partially filled the orbitals. So within those orbitals, there can be electronic transfer from the highest occupied molecular orbital to the lowest unoccupied molecular orbital. Alright, so these are the types of electronic transitions that can be seen under electronic, that may cause electronic spectra. Alright, of course, and then we have to talk about Beer-Lambert theory. Beer-Lambert theory is the theory that is guiding absorption, all absorptions. You know, when a molecule absorbs energy, you know, in order to relate the amount of light entering the substance, that is the absorbance, you know, to the concentration of the solution, you use Beer-Lambert law or Beer-Lambert theory. And it says that absorbance is directly proportional to the concentration of the solution and the path length, you understand, and the path length of the cuvette that was used. Invariably A is equal to ECl. Alright? Alright? So this is basically what Beer-Lambert's law is all about. Alright? All of this may be under, you know, introduction. But what we are really interested in are these 4 items. Those are the areas that many students find difficult due to experience in time past.